Assalamu alaikum. Inshallah, today we will continue same subject, graph theory. I think last time we stopped around this area here. Okay. We took some examples last time to draw graphs. We take example A, B, C, and I give you example D to try it at home. Anyone tried to solve example D? Last time we take this example 1, A, B, C. Anyone tried example B? We will try now to see if we can solve it or not. It's good that you tried, Mustafa. Okay, just to repeat again. When we speak about edge, okay, we said any graph have vertices, which is the node, and edge, which connected between nodes. So if we have 5 edge, for example, then we have 10 degrees available. Why? Because each edge will connect between 2 vertices. So each edge will add 1 degree to this vertices and 1 degree to this vertices. So each edge will add 2 degrees. Even if we have loop, it will add 2 for same vertices. It will add 1, 2 degrees. So the best way to answer this type of examples, we have number of vertices, we have number of edge. We can identify for each vertices how many edge can be out or in, because we speak about undirected graph, so doesn't matter it's out or in. So if we have 5 edges, this means we have 10 degree, and we have 4 vertices, V1, V2, V3, and V4, and the total degree, summation of the degree for all the vertices will equal 10, depending on number of degrees, edges, because each edge will connect 2 vertices or same vertices. So each edge will add 2 degrees. So if we have 5 edges, this means we have 10 degrees. Okay, I said I need all vertices to be odd. So it could be 1, 3, 3, 3, the degree for all vertices. It could be 5, 3, 1, 1. So we have more than one answer, actually. But if you look to this one, 5, 3, 1, 1, and 1, 3, 3, 3. I think this one could be much easier. So we have 3 vertices and 4 vertices. This one, 1, 2, 3. So each one now 2. We can connect between these two. So this one have 1 degree. This one, let me make it like this. This one have 3. Still, this one have 2. This one have 2, and we have one more edge. So we can make it like this. So this one odd, this one odd, this one odd, this one odd, and we have 1, 2, 3, 4, 5 edges. If we want to answer this one, we have 3 edges, no loops. So if we want to answer it, first we need to know how many degrees. 3 edges, this means total for all vertices, 6 degrees. And we have 4 vertices. So we have V1 plus V2, the degree for all of them, plus V3 plus V4 will equal, the degree for them will equal 6, and all of them odd. So it could be 3, 1, 1, 1. So if we understand this, V1 to be 3 and all 1, so we can connect V1 with V2, V1 with V3, V1 with V4. So it's like this. We have 1 in the center and we have 3 vertices. So like this, we have 1, 2, 3, 3 edges and all odd, 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 odd. 3, 1, 1, 1. Here's the degree 1, 2, 3. The degree here 1, the degree here 1, the degree here 1. Also, we give this example, same idea. Let's go directly to this example. Actually, this example have problem. I will mention what's the problem here. Okay, look, we have 4 edges. So we have 8 degrees. Actually, this 8 degrees cannot have only one odd. Try, if it's have 1 odd, there remains 7 odd. So we will have another odd. Okay, let's try 3. If we have 3, what does that remain? Degrees 5. 5 also odd, so we cannot have 3 all even. Same idea, if we have 5, still 3. If we have 7, still 1. You cannot divide 1 for 3 vertices. So you cannot answer this one. Oh, sorry. You cannot answer this one. Why you cannot answer this one? Because actually, if you think little bit, you will know why you cannot answer this one. When we said we have 1 vertices odd, only 1 vertices odd, but we know that each edge have vertices in the sides. So you cannot have 1 vertices odd, because this odd vertices will be connected with another vertices. So number of odd vertices should be even. You can have 2 odd vertices, you can have 4 odd vertices, you can have 6 odd vertices, but you cannot have 1 odd vertices. You cannot have 3 odd vertices. You cannot have 5 odd vertices in any graph. So, number of odd vertices should be even. So, graph could have 2 odd vertices, 0, 2, 4, 6, 8, but cannot have 1, 3, 5, or 7 odd vertices. Okay, there's a theorem for this. We will take it. So you cannot draw this one. D, you cannot draw it. Why? Because there is exactly 1 odd vertices, so we cannot draw this graph. Okay, so we have hand check theorem. From its name, hand check theorem, why they called it hand check? Because hand check, it's between 2 peoples, yes? When you make hand check, it's between 2 peoples. Same idea. Any edge will connect 2 sides, will connect 2 vertices. So it's like hand check. Each edge will will connect 2 vertices or same vertices but from 2 sides. So each edge will add 2. Each edge will add 2 vertices, 2 degrees for the summation of the edges or of the degrees. What is the degree? Degree number of edge, total number, degree for each vertices, each node. It's the number of edges from this node. The total number of degrees will be 2m if m is the number of edges. So the theorem said, if we have a graph V capital, and have edges, of course, we speak until now about undirected graph. What's the meaning of undirected graph? This means doesn't matter the direction of the edges, okay? With m edges, so number of edges m, then 2m, same. We used here in this example this theorem, but now we know how to write the theorem. It said 2m, so 2 multiplied by number of edge equals the summation of all the degrees for all the vertices. So if we have 3 vertices, V1, V2, V3, so 2m, which is double the number of edges, equal degree of V1 plus degree of V2 plus degree of V3, and so on, plus degree of Vn if we have n vertices. This same when we said 4 edges, so we have 2m, so the total number of degrees will be 8. If we have 5 edges, 2m, this means we have 10 as total number of degrees. Same here, we have 6 as total number of degrees. Okay, so in this example, how many edges are there in a graph with 10 vertices, number of vertices 10, of degree 6? So each vertices have, so we have graph like this, have 6 vertices, each one of degree 6, have 10 vertices, each one with degree 6, 1, 2, 3, 4, 5, 6, like this. So the total number or the summation of all the degrees will be number of vertices, which is 10, multiplied by degree of each one, which is 6. So we have total number of degrees, or the summation of the all degrees will be 6 multiplied by 10, because we have 10 vertices and the degree of each vertex is 6, so the total will be 60. According to hand-check theorem, which tell us that 2m equals summation of degrees for all vertices, which is 60 from here. So m, which is the number of edge, will be 30. So how many edges? We have 30 edges because 2m equals 60, according to hand-check theorem. Okay, if a graph have 5 vertices, can each vertex have degree 3? Okay, this is good question. We have a graph with 5 vertices. The question, can each vertices have 3 degrees? So let us check according to hand-check theory. The total number of degrees, if we have 5 vertices, each with the 3 degree, equal 5 multiplied by 3, which is equal 15. Yes? And we said 2m equal the summation for degree for all the vertices. So it will equal 15. So 2m equal 15, but we know that 2m, it's even number should be. But 15 is odd. So this is wrong. Then we cannot have 5 vertices all with degree 3. Because we cannot have like this. If 2m equal 15, this means number of edge 7.5. Is there a half edge? It's wrong. We cannot have 7.5 number of edges. Number of edges should be integer, 1, 2, 3, 4, and so on. Okay, depending on this, we have another theorem. This theorem said if we have undirected graph, or in another term, an undirected graph should have even number of vertices of odd degree. So number of odd degree vertices should be even. So in any graph, we can have 0 odd vertices, as I mentioned before, 2 odd vertices, okay, 4, 6, and so on. But you cannot have odd degree, like number of odd degree 1 or 3 or 5. Why? Because each edge should connect 2 vertices, so the total number of odd vertices should be even. And if we return to this example, when we said 5 vertices, each one have 3 degrees, this means we have 5 odd vertices, and this cannot be. 5 odd, this means odd number of odd vertices, but we said we should have even number of odd vertices. Okay, so according to this theorem, this graph cannot be drawn. Why? Because we have 1 odd vertices, and this is impossible. We cannot have odd number of odd vertices. We should have even number of odd vertices. Like here, all odd, we have 4 vertices, so it's even number of odd degree vertices. Same here. So if I said here, instead of this example like this, if I said 2, it have 2 odd vertices, we can answer this. If we said we have 2 odd vertices, actually this same question like this one. Because when you have 2 odd vertices, this mean, and you have 3, this mean you have 1 even. So number of degrees here will be 8, because we have 4 edges. We have 2 odd, so we can have 2, 3, 3, and we can answer this easily. This 3 vertices, 2 odd and 1 even, so we can have like this for 3 vertices and this 1 odd, 1 even and 2 odd. Okay, good. We usually in computer science or in computer, of course, in the memory, you will not store the graph like this. How to use or store or represent the graph? Usually we use something we called it adjacency matrix. This matrix, it's a square matrix to represent the graph. Usually in computer programs, we can represent the graph as adjacency matrix. It's a square matrix. Square, this means 2 dimension, same size. 1, 2, 3, 4, 5 elements. 1, 2, 3, 4, 5 elements. So the elements of the matrix indicate whether pairs of vertices, 2 vertices, each 2 vertices, are adjacent or not, are neighbor or not. Adjacent, we already mentioned it last lecture. This means 2 vertices neighbors or adjacent or not. How to know if they are adjacent or not? If they are connected with edge. So we have all vertices as the columns and all the vertices as row, and we will see the connection between each two vertices. For example, between V1 and V2, there is 1, 2 connection. So this number of edges between two vertices. Why? Because it's undirected graph. That's why we have 2. Because from this side, V1 to V1, or we can write it V1 to V1, the other side. The direction doesn't matter, so we have 2 connection from V1 to V1. Okay. From V1 to V2, V1, V2, we have 1 edge. V1 to V3, there's no connection, so 0 edge. V1 to V4, no connection. V1 to V5, no connection. Now, V2 with V1 have 1 connection. So you will have here this column and this row should be same. Because V4, V1, it's undirected graph. Do we have problem with connection? Okay, wait 1 second. Let me check the connection. Okay, it's okay. I think we had small connection problem, but it's should be okay now. Okay, let's continue. So it's like this idea. So between V3 and V1, same, no connection. V3, V2, there's V3, V2, there's 1 connection, and so on. You check V3 with V5. We have 2 connection, V3, V5. There's E3 and E5. So we have 2. This number of edge between the 2 vertices. We call this adjacency matrix. Okay. Until now, we spoke about undirected graph. The different little bit, there's not too much different between directed and undirected graph. Directed graph, it's take in consideration the direction of the edge. So a set of node, this is a directed graph, is a set of node connected by edges, where the edge have a direction associated with them. So we have like arcs connected between two vertices. For example, arc XY. This means we have direction from X to Y. And if we said Y arc YX, this means a direction from Y to X. Okay, so if we have directed graph, for example, here there's small changes in the matrix. You see here, because doesn't matter. So V1 from V1 to V1, it's same like from this V1 to this one. From V3 to V5, same like from V5 to V3. Why? Because same value. See? Why? Because direction doesn't matter. But if we speak about adjacency matrix with a directed graph, now it's matter. So we have here one direction. So between V1 and V1, there's one way. So we have one edge, V1 to V2, V1 to V2, V1 to V2. There is no edge because the edge here, it's from V2 to V1. That's the difference here. So we don't have from V1 to V2, from V1 to V3 to V4 to V5. From V2 to V1, now we have this E1. So this is a different. Here, when direction doesn't matter for undirected graph, so from V1 to V2, there is the edge, E1. And from V2 to V1, same edge. It's two direction. It's because it's undirected graph. Here, no. From V1 to V2, we consider that there's no edge. Why? Because the direction it's come from V2 to V1. Even let's check now V3 with V5. From V3 to V5, there's one direction only, which is here, E3. This one not considered. Why? Because it's the opposite direction. And from V5 to V3, also not 2, it's 1, because E3 not considered a directed from V5 to V3. So we have only E5. Okay. Sometimes we have width, like for example, the distant, or sometimes, as we mentioned last time, we can present any idea from the real life as a graph. For example, if we said friends, okay, we have Ali, friend with Ahmad, friend with Omar, and we have Omar, friend with Nihad, and we have Lana, friend with Omar, and so on. We can present this as a graph. So we can consider it like this. We have Ali, he's a friend with Ahmad. So there is edge between them. He friend with Omar. So there is a bridge between them. We can anything in real life that have a relation between things, between edge, between entities, between objects from the real life, we can present it as a graph. We have, for example, here Nihad. So Omar friend with Nihad. We have Lana, friend with Omar. We can have also Nihad, for example, friend with Lana. So there's connection. So we can present it as a graph. So anything from real life, we can present it as a graph. If the connection between this vertex or objects have values, so we can put these values as a weight for the direction or for the edges. For example, if we consider this city 1 and this city 2, we can consider this the distance. For example, in miles, 2 miles or something like this. So we can present the cities and the distance between them on a graph like this. It's important to have actually graph with widths on it. So here we have this graph with width presented in each edge. So from V1 to V1, we have one edge with 3, the width of it. From V2 to V3, for example, we have one direction with 2, and so on. So we can present in the matrix the connection by take the width of this connection. Okay, now we come for playing to make it more interesting. Okay, we have something called a traversable graph. A graph is a traversable if you can draw a path between all the vertices without retracing same path. So the idea that this graph is traversable if you can draw all the edges, all the path without retracing or without pass the same path, the same edge 2 times, only 1 time. I will give you example. You can trace this graph. I can trace it. What's the meaning of trace it? Trace it. Use your pen without removing it from the paper to connect all the edges, but you should not trace the same edge 2 times. Let me try it. I will trace this one from B, C, D, A. Okay, I will start from here. Okay, I pass all the edges without passing the same edge 2 times. Let me another time. So the idea, the graph is a traversable graph if you can draw a path between all the vertices, or you have to pass all the vertices without tracing the same path or the same edge 2 times, without retracing the same path. So there is another solution. I can pass from D to C, then C to B. So we have D, C, B. Okay, then I can go through BD, then DA, then another time AB. So I trace all the paths only one time, without removing the pen, like this. One time. So now let's playing with each other a little bit, yes. So I need one from you to trace this one. Let me draw it for you here on the whiteboard. Okay, whiteboard, where is it? Okay, we have this graph. I need one of you to use the red pen to trace this graph. This means draw this graph without passing the same edge 2 times. Anyone want to try? Should raise his hand first. I don't want to make... Anyone want to try? I will try this one for you. If anyone don't... to show you, I want to trace everything here. This means I want to draw all the edge without removing my pen and without passing same edge 2 times. I will start from here. Okay, this first edge, second edge, okay, third edge, fourth edge, okay, okay. Oh, this is wrong. I will try another time. Do we have someone want to try? Raise your hand before trying. I need only one. Okay, I will try. Okay, see, last time I lose it. I did not successfully trace it. I will successfully trace it now. You see, I will start from here. Okay, okay, until one. Okay, okay, successfully traced it. Another one want to try? I can trace it another time successfully. I can start from here. Okay. Okay, I will do like this. Okay, good. This is the meaning of tracing. To draw the edges or to pass all the edges without retry or without retrace or without passing the same edge again. I don't know what's the problem, but I will try again for you. Let me just. I will trace it here for you. Okay, check here. This is the same graph. I will trace it. So I can start from here. Okay. I will pass this one. Then this one. This one. This one. I did not pass the same edge again. You can enter same vertices, but do not draw same edge again. Okay. 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 So this one traversable. Why it's traversable? Because I can draw a path between all the vertices. Now I draw a path between all the vertices without retracing or redrawing the same path again or the same edge again. So this one traversable. We can try with this one, but I will tell you this one not traversable. You cannot. If you try hard, if you try as much as you cannot traverse this one. Let me try. This one option, yes. Okay, this edge, we cannot pass it. Why? Because if I want to return to it, I have to pass this one or return again. So it's not traversable. If you try anyway, it will not traversable. Anyone want to try this one? I can share it here. I will draw it for you and you can try it. This is a whiteboard. Okay, I will draw it. As I remember, it's like this. You can use the red pen. Anyone want to try? You can raise your hand before trying to traverse this one. You understand what's the meaning of a traversable graph? Anyone do not understand what's the meaning of a traversable graph? How many students around me here? 20 students, but no one answers this. Even no one told me if he understand or not understand what's the meaning of a traversable. It's a game. We was playing it when we was kids to traverse or to draw this. Okay, you can draw this one again without removing your pen from the paper and without drawing same edge 2 times. This is the meaning of a traversable. Anyone want to try? Okay, I will do it myself. I show you many examples. What about these 2 examples? I already show you this example. I want to traverse this one. I can draw it again or I can pass it again from D and return to D, like this. Okay, like this. I traverse it, I draw it again without removing my pen. Okay, I will answer this one also. Okay, I can start from anywhere actually. I will start from F, D, C, E, B, C, A, B, D, A again, and F. I traverse it. Is there any other direction to traverse it? Yes. You can do it many ways. Anyone want to try this another way? You don't need to show the movement. You can see this one from A to C. Sorry. I did not. I did not share my screen again. I forget to share my screen again. Okay, you correct. So I can traverse this one. How to traverse this one? This means draw it again or draw over all the edge without passing the same edge or without retracing the same edge again. So I will draw it like this from D to C, from C to E, from E to B, maybe from B to C, C to A to B, and B to D, T to A. So I draw it again. So this one traversable. This one not traversable. This one traversable. This one traversable. This one not traversable. You cannot draw it again. I will tell you why. We have some theorem for this. But this one that I draw for you here on the whiteboard, it's traversable. Anyone want to try to traverse it? Here. You have the control. You can use red color to traverse it. Yes, Isra, you can try. Use the red color. You are trying or not? Okay, I saw the last. I saw the result, but I don't know if you traverse it correctly, but it's a traversable, so you can traverse it correctly. Anyone want to try this one? I will draw another one. Anyone want to try this one? using red color. Yes, go ahead. Yes, Mustafa. Actually, it's not traversable. Sorry, it's a traversable. Let me check. 1, 2, 3, 1, 2, 3. 1, 2. No, it's a traversable. But you should know how to traverse it. You should know how to traverse it. So let us take some information about a traversable. There is some theories. Okay, you can try it. I will give you the opportunity to try it. Use red color. Okay. Okay, so far correct. 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 Yes, that's correct. Why? I will give you a small hint before we reach this idea. You see this edge, this vertices, it's odd. And this vertices is odd. If you have only two odds or zero odd, it's a traversable. If you have more than two odd vertices, it's not a traversable. And if you have zero odd vertices, doesn't matter from where to start. If you have two odd vertices, you should start from one and end on the other one. So you started from here and you ended here. There is algorithm to do this. We will take this algorithm, inshallah. How to traverse a graph. I know it's funny and some students will say, oh, what's this? Why we need this? Actually, there is many real life problem using graphs and using traversable graphs. For example, you want to visit some baths, you are shopping in the center. For example, you are shopping in some city and you don't want to enter the same road, the same path 2 times. So you can look to the map, connect between the edges between the roads and said, I will pass here, here, here. So you will use as a traversable graph. I cannot. One? No, this one not odd. 1, 2, 3, 4. It have 4. It's not odd. So let us now go to more issues about traversable graph. There is some theories from one of the famous mathematical scientist. His name Euler. I don't know how to pronounce his name actually. It's difficult for us to pronounce it. Okay, let us pronounce him Euler or Euler, something like this. Anyway, this one found that there is something called a path or Euler path. Euler path contain each edge of the graph. If you have a graph, each edge of the graph exactly one. If you have each edge, all the edge of the graph exactly one, this means you did not retrace the same path. So this graph will be traversable, yes? So according to Euler, Euler path is a path that contains each edge of the graph exactly once and each vertex at least once. So you can have the vertex more than one time, it's okay, but each edge should be exactly once. A connected graph is said to be traversable if it's contain an Euler path. And what Euler said, the path will be Euler path and traversable if it's only have two odd vertices. So if you look to any graph, it have two odd vertices, then it's Euler path. Any graph have two odd vertices, it's Euler path. If it's Euler path, then it's traversable. So to check any graph, if it's traversable, first look to it. If it's have two odd vertices, then it's Euler path. If it's Euler path, then it's traversable. So let's check this one. How many odd vertices we have in this one? Let's name this first one, second one, third one. How many odd vertices we have here in graph 1? 4. 4 odd. So it's not Euler path. That's why it's not traversable. Okay. How many odd in graph 2 we have here? We have 1, 2, 3. This one odd. 1, 2, 3. This one odd. This one even. This one even. This one even. So we have 2 odd. So it's Euler path. So according to Euler, graph 2, it's Euler path. So it's a traversable. Okay, let's check this one. how many odd? Actually, in this one, we have 0 in graph number 3. We have 0 odd. So it's not Euler path. Yes? But it's traversable. Why? Because there is another thing founded by Euler called Euler circuit. Okay. Euler circuit said in an Euler path, actually here, just to be not confused, Euler path, okay, contains each edge exactly once, and each vertices at least once time. Okay, good. This is the Euler path, but I mean for traversable Euler path, a connected graph is said to be traversable if it contains Euler path. So, to be traversable Euler path, it should have only 2 odds. You have to focus here for the 2 odd. Here in Euler circuit, if the starting vertices, it's important, the starting vertices is the same as its ending vertices. This means you start and end at the same time. There is many things in the real life start and end in the same vertex, the same node. For example, you have your boat, hopefully, yes, and in the sea, you have some cities, and you want to visit all cities. You started from A. Of course, this is your hometown. You will visit all that cities and return to your home town. So there is many things in real life that started from same point and return to the same point. So if you have something like this, you want to start from the same, start from one vertex and end at the same vertex. So if this vertex A, you want to return to the vertex A without passing same edge 2 times. We call this Euler circuit. And Euler circuit is traversable if all vertices are even. So, Euler path, to be traversable, it should have 2 odd vertices. Euler circuit, to be traversable, it should have all even. So it should have 0 odd vertices. That's why for a graph to be traversable, if it's have 2 odd or 0 odd. Any graph have more than 2 odd vertices will not be traversable. if it have 0 odd, this means all the vertices from the degree even, it's traversable. If you have 2 odd, it's traversable. If it have 2 odd, it's traversable because it's a lower path. If it have 0 odd, it's traversable because it's a lower circuit. Why it's named a lower circuit? Because it start and end at the same vertex. Same vertex. So it's like circle. What's the meaning of circle? You start from this point and return to the same point. It's circuit. Same idea. A lower circuit, it's a path that is starting and ending with the same vertex. Okay. And it will be traversable if it's have all vertices with even degree. So according to this one, we will look to the graph. If it's have 2 like this, have 2 odd, it's traversable because it's a lower path. 0, this one have 0 odd, so it's traversable because it's a lower circuit. This one have 4 odd, it's not traversable. You cannot draw it without removing the pen and without retracing the same path. Why? Because it's not a lower path and it's not a lower circuit. Okay, so we have graphs A, B, C, D, E, F. D, E, F, we already answered them. Which of A, B, C, a lower path, which is a lower circuit, which is traversable? I need your answer. What is the first question you have to ask yourself? You have to know number of odd degree vertices for each graph. Number of odd degree vertices for each graph. So for graph A, what is the number of odd vertices? This one even, this one even, this not 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 even. So graph A have 0 odd. Vertices. So is it traversable or not? And why? So A, is it traversable or not? And why? Not traversable? Am I speaking with myself? What's the meaning if it have 0 odd? It's a lower circuit. We said if the graph have 0 odd, it's a lower circuit. And if it a lower circuit with 0 odd, then it's a traversable. it's traversable. So A have 0 odd. That's why it's Euler circuit. And because it's Euler circuit, it's traversable. Yes, and we said it's have 0 odd, Hassan. Hassan, we said it have 0 odd. If it's have 0 odd, so it's a Euler circuit and it's traversable. Okay, what about B? Hassan, try to answer B, please. Okay. You should not say I think. You should know why. It's not traversable. Why? Because yes, as Isra mentioned, we have 4 odd. We have 4 odd. So it's not a Euler circuit. It's not Euler bus. So it's not traversable. What about C? Is it traversable or not traversable? And why? Yes, I speak now about C. What's the first question you have to ask yourself if you want to check if it's traversable or not? Number of odd edges. Actually, C have how many odd? It's have 0 odd. It have 0 odd. What's this mean? Okay, good answer. So it have 0 odd. This mean it's a traversable because it's Euler circuit. Good. Okay, let me make small change. Okay, you see this one? I want to connect here. Let me just remove all this. Okay, after my connection, let me connect with the same color. I will use the same color. I need answer now. Is it Euler or not Euler after my change? I speak about C. Is it traversable or not? C after my changes. Is it traversable? Okay, traversable, but why? The first answer, the first step should be number of odd. how many odd vertices in C. Now, after my changes. 2 odd. What's the meaning of having 2 odd vertices? Is it Euler circuit or Euler path? Okay, good. So it's Euler path. And because it's Euler path, it's traversable. I can traverse it even. Okay, you see it's complicated, yes? But it's very easy to traverse it. Just starting from one odd and end with the other one. So I will start from this odd. You see, it's traversable. Okay, now just another
52 37 0 64.
6 altmış dört. Yes. But it's better to turn off your mic. Okay. I will make another change here. And I will ask the same question. Is it traversable now? Graph C. And why? And why? Okay, not traversable. Why? To answer this, you have to mention how many odd vertices. How many odd vertices now? It's 4. 1, 2, 3, 4. So it's not Euler path, it's not Euler circuit. So it's not traversable. Same idea for D. We have 1, 2, 3, 4 odd. That's why it's not traversable. For E, it's traversable because we have 1, 2. So it's Euler path. For F, it's traversable because we have 0 odd. So it's Euler circuit. Okay. To traverse Euler circuit or Euler path, this one Euler path, this one Euler circuit. Of course, here, if you look here, it's not Euler circuit. If we have another edge like this one, it become Euler circuit. Why it's become Euler circuit? Because now we have 0 odd. Before this, it's have 2 odd. So we can traverse it easy. We already show. We have algorithm actually. So let's take the algorithm directly of how to traverse a graph. Okay, this just like gathering all the information. If a graph have an Euler path, then it must have exactly 2 odd vertices. If number of odd vertices anything other 2, then it's not a Euler path. Okay. If a graph have a Euler circuit, then it must have all even vertices, then 0 odd. If a number of odd vertices in a graph anything except 0, then it's not a Euler circuit. Okay, so if 2 odd, it's a Euler path. 0 odd, it's a Euler circuit. If it's a Euler circuit or a Euler path, it's traversable. It's traversable. If you need this, but you cannot come in the exam, for example, and consider a new path or a new edge from yourself and change the answer. Okay. So yes, if you add one edge to a Euler path, it's become a Euler circuit. And if you add one edge, but you have to focus. If you add one edge to a Euler path between the two odd. Here we have this one odd, we have this one odd. If you add edge between two odds, so this become even and this become even, so all become even. So it's become a Euler circuit. But if you add the edge here, for example, between A and E, it will not become a Euler circuit, because you, like this, you will have 1, 2, 3, 4 odd. It's not a Euler circuit, not a Euler edge. So to convert a Euler path to a Euler circuit, you can connect extra path between the two odds. We have here two odds, so we can connect them. So this become even and this become even. So it become a Euler circuit. The opposite, it's correct. You can connect any two vertex from the Euler path. It will convert it to Euler circuit. From Euler circuit, it will connect it to Euler path. But from Euler path to Euler circuit, you can only connect the two odds to become a Euler circuit. Don't trouble yourself. I will not ask like this. So just this for fun information, okay? How to convert from Euler path to Euler circuit. I will not ask you to convert. Okay. So you can try to think about this questions. Does every graph with 0 odd vertices have an Euler circuit? Does every graph with 2 odd vertices have an Euler path? Try to check it at your home, okay? Is it possible for a graph to have just one odd vertices? Of course, we answer this. It's not possible. We already answered this one. When we mentioned the hand check theorem, we said we cannot have one odd vertex, because number of odd vertex should be even. We can have 0 odd, 2 odd, 4 odd, 6 odd, 8 odd, 10 odd vertex or vertices, but we cannot have 1 or 3 odd, or even 5 or 7 odd. Okay. Another interesting subject. Also, we still have some fun here, but it's in the real life, it has some famous applications. We will take some problem and solve it using this theories. There is something called a bridge. If you know, if you have like this, for example, if you have island and the mainland, you can connect between them using bridge. If you destroy this bridge, there is no more connection here. Yes. So in graph, we have same idea. We have the term bridge. You need to know this term. What is the bridge? A bridge, if you remove this type of edge, actually the bridge is an edge. But if you remove this edge from connected graph, it can make it disconnected. This edge that if you remove it and the graph become disconnected, we called it a bridge. In this graph, how many bridges we have? We can check. If we remove this one, is it still connected or become disconnected? What's the meaning of connected? Meaning that all the nodes have connection with some other nodes. So if we remove, for example, this one, it's still connected. So this edge, not a bridge. Okay, another example. If we remove this one, we still can reach this one, we can reach this one, we can reach this one. So it's still connected. So this not a bridge. Okay, see this one, if we remove this one, is it still connected graph? No. Why? If we remove this one, we cannot reach this vertex. So if we come from here, we can come here, this bridge broken, we cannot reach here. So this edge is a bridge. If we remove it, it becomes disconnected graph. This edge also a bridge. If you remove it, you will make the graph into another two graphs. So it becomes disconnected. This edge also a bridge. This edge also a bridge, because if you remove this edge, if you destroy it, the graph become disconnected. So it's become one and another graph. You cannot move from this graph to this graph. Why? Because you already burned or destroyed or removed this bridge. This is the idea of a bridge, and we need it actually in some theories. Here, this is the algorithm that will make you able to trace any Euler path or circuit. Now you can return to your friends, you can return to your family and play with them, bring any graph and said, okay, trace this graph. Even if the graph is traceable, some people will find it very difficult to trace it. After this algorithm, Fleury algorithm, you will find it very easy to trace any graph. Okay, so to trace any graph, first we want to know if it's Euler path or Euler circuit. If it's Euler path or Euler circuit, it's traversable. We will use Fleury algorithm to traverse it. What the Fleury algorithm said? It said, make sure first that the graph have 0 or 2 odd vertices. If it's 0 vertices, then it's Euler circuit and it can be traversable. If it have 2 odd, so it's Euler path and it's traversable. If it have more than 2, then it's not traversable because it's not Euler path or Euler circuit. Good. Then what to do for tracing if it's Euler path or Euler circuit? Second step, if it's 0 odd, you can start anywhere from the graph. If there is 2 odd, you have to start at one of these two odd. You have to start from one of the odd vertices. If we have 0 odd, you can start anywhere. If we have 2 odd, you have to start from one of the 2 odd. Like in this graph. Like in this graph, we have 2 odds, A and D. If you start anywhere except A and D, you will not be able in any way to traverse this graph. You should start from A or D. If you have like this. Why? Because A and D odd, you have to start from one of them. So if you start like this, for example, I will start from F. I will not be able to trace this one. You see, I stopped here. Or I will stop here. Or it will not, you will not be able to trace it. To trace it, you should start from one of the odd and end in the second one. So I will start from D or from A, for example, from A. Okay. Then I end with D. If you start from A, you will end at D. If you start from D, you will end at A. If you have like this, 0 odd, you can start from anywhere. Okay, so this is step number 2 in the algorithm. If you have 0, start anywhere. If you have 2 odd, start from one of them. Then follow the edges one by one. Okay, but you have something here. If you have some points like this, you will have to choose between 2 edges or 3 edges or 4 edges, which one I should follow? This one or this one or this one? Actually, you have to ask yourself, if I have any bridge, what's the meaning of a bridge? A bridge, if I remove it, the graph will become disconnected. So if you have choices between edges, you have to ask yourself, do I have any bridge? If you have choices between a bridge and non-bridge, you have to choose always non-bridge. In another term, don't burn your bridge, because if you burn your bridge, if you pass your bridge, you will lose the connection for your graph. So if you have to choose between a bridge and non-bridge, you have to choose non-bridge. Okay, stop when you run out all the edges, if you pass all the edges. I will give example here. We have this graph. Then we will find a loop path or circuit in this graph. Actually, is it a loop path or circuit? We will answer this by finding number of odd. So this one odd, this one even, this one odd, this one 1 2 3 4 even, this one 1 2 3 4 even, this one 1 2 3 4 even. So we have 2 odd, then it's a lower path. Now the question, find Euler path. In another term, traverse this graph. You see this graph, it's complicated. And it's difficult to traverse it without following this algorithm. So we will follow the algorithm. Where is the first step? Okay, it's a lower path. Second step, we have 2 odd, then we should start at one of them. So we have 2 odd, A and F. We have to start from A or F. Okay, then there are 2 odd vertices, A and F. We will start from A or from F according to Flory algorithm. We will start from A or F. I will start from F. Okay, then we choose F to start from it. So first node in the Euler path will be F. Okay, continue. We started from F. Every time we will delete the edge that we will choose it because we don't want to pass the same edge again. So we have 3 choices. We can go from F to D. We can go from F to C. We can go from F to E. Any one of these edges consider as a bridge? No. We can delete this without any problem. We can delete this without any problem. We can delete this without any problem. So I'm free to choose anyone from C. I will start from F. I can go to D, C, or E. Why? because all of them not a bridge, non-abridge. Okay, so we will move from F to E. We will delete this one. So the path now, F, E. Now we reach E. From E, we don't have any choice. Actually, from E to A, this a bridge. This is a bridge according to our definition. It's a bridge because removing it will make the graph disconnected, yes? But we don't have any choices. We are at E, and we just have this bridge, so we can burn this bridge. Why? Because we don't have choices. But if you have to choose between a bridge and non-bridge, you have to choose non-bridge. Here, I don't have any choice. I have to pass from E to A, so I will burn this bridge without any problem. I will reach now A. F, E, then A. Okay, I deleted this one. Now look here. I can move from A to B. I can move from A to C. If I delete this one, it's okay because it's non-bridge. If I delete this one, it's okay because it's non-bridge, so doesn't matter. You can choose from A to B. You can choose from A to C. Okay, so we will choose from A to C. You can choose to B, it's okay. So the path E, F, A, C. Okay, good. Now I'm at C. At C, you can move to B, you can move to A, you can move to F. It's non-bridge, 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 so you can take anyone. So I will take from C to B. Now we are at B. Look, from B. From B, you can move from B to D using this one. From B to D using this one. Or you can move from B to A. At this point, you have a problem. Why? If you moved from B to A, then you burn this bridge or you delete this bridge because from B to A, it's a bridge. Why it's a bridge? Because if you delete it, now A not connected. You reach E from B to A, you are now at A, but you cannot move to another place. So this graph become not connected. So if you have situation like this, you have non-bridge here from B to D, you have non-bridge from B to D, and you have a bridge from B to A. Do not burn this bridge if you have other choices. If you don't have any choice, it's okay. But we have an unbridged choice, so we cannot choose from B to A. We have to choose from B to D. Okay, so now in this step, crossing edge BA would be a mistake. Why? Because we will stuck at A and we cannot return to the graph. Why? Because BA is a bridge. Removing it will make the graph disconnected. And we don't want to cross a bridge. We don't want to burn a bridge. Unless the only way to burn a bridge. Okay, let me just move it quickly. This last example. And we almost finished, just 1 minute. So if we have only this edge to move, then we can burn it a bridge. But we have other choices, so no need to burn the bridge. We will move from B to D. So from B, we will move to D. We can burn this one or this one. We choose to burn this one. Okay, another time we are at D. We have this to choose. From D to B, from D to A to C, from D to F. Actually, from D to B, it's a bridge. And we have another choice from D to C and D to F, non-bridge. Do not burn the bridge if you have, or do not cross the bridge if you have another choice. So I will choose from D to C or from D to F. It doesn't matter. We will choose from D to C, from D to C. Okay, so from D to C. Now from C to F, we don't, it's a bridge, okay, but we don't have any other choices. So we will delete from C to F. Okay, from C to F, it's a bridge, but we don't have other choice. Same way from F to D, it's a bridge, but we don't have other choice. And from D to B, and from B to A. So the Euler path, this is the final answer. The Euler path will be F, E, A, C, B, D until E. So from F until A, we reach all the passes. We start from odd and we return to the odd. And this is the Euler path. This is all for today. Thank you. See you inshallah next week and have a nice week. I will try to give you a quiz next week inshallah. So in this subject, I will try to give you a quiz just to train you about some type of exercises. Okay, see you. Assalamu alaikum.